David Can here with a question in topic 6.1, circular motion. In this question, what we're going to be doing is looking at a lot of different properties of circular motion. We'll be looking at period, frequency, angular displacement, angular velocity. We'll also be looking at centripetal acceleration, period, frequency, lots of different things. So we'll cover a lot of different things, but only at a sort of light level, because none of these individual topics are particularly complicated. But we'll see how they all come together in this question. In this question, we have a body which travels with a constant speed of 2 meters per second around a circle with a radius of 5 meters, and we're asked to calculate a lot of different things. So just to help us visualize what's happening here, we have a circular path with some sort of body, whatever it is. We'll make it a little brick. And it's traveling along that path at a speed of 2 meters per second. The path itself has a radius of 5 meters, and we're asked to calculate things such as the distance moved in one revolution. One revolution is all the way around the circle and back to the beginning, so the distance is the circumference of the circle. And circumference of a circle is calculated with 2 pi times the radius of the circle. That's 2 pi times 5 meters. So that's 10 pi meters. Pi is 3.14 or something, 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 something. So that's 31.4 meters all the way around. Next part is part B. Part B is the displacement in one revolution. And at first glance, this almost looks like they asked us the same thing twice. They want the distance, now they want the displacement. But we have to remember that the distance is just the length of travel along the path of travel, so that would be the circumference of the circle. But the displacement is the straight line distance from start to finish, and it doesn't really care how you got there. It just wants to know how far you are from where you started. So if the body starts here and goes all the way around and winds up here, it hasn't gone anywhere. It's right back where it started. So the total displacement is actually 0 meters. It winds up going nowhere. It doesn't matter that it traveled 31.4 meters to get nowhere. It's gone nowhere. Part C asks us for the time taken for one revolution. So we need to know how long is it going to take to go all the way around this circle. We're going to work with speed is distance traveled divided by time taken, and it's this time taken we want to solve for. Because we know the speed, it's 2 meters per second, and we know how far we go, 31.4 meters. So we'll rearrange to solve for t. Multiply across by t, and then divide by s, and we get that the time taken is the distance traveled divided by the speed of the body. The body travels 31.4 meters at a rate of 2 meters per second. 31.4 divided by 2 is 15.7. Meters cancel with meters, and 1 over per seconds is just seconds, 15.7 seconds. Part D asks us for the frequency of the motion. Okay. Well, the frequency is very closely related to the time taken for one complete revolution, which is what we found in part C. The frequency is the number of complete rotations per second, whereas the time taken for one complete revolution is the number of seconds per complete revolution. That they're opposites. Frequency is rotations per second, and period is seconds per rotation. This means that the frequency is 1 over the period. And I'll use a capital T here rather than a lowercase t, capital T usually for period. But it's the same T as over here. So the frequency is just 1 divided by 15.7 seconds. And that works out to 0.0637 per seconds. Per seconds, there's a special unit for that. It's hertz. Either answer would be fine. Part E asks for the angular velocity. Angular velocity is the number of radians crossed per second. It's a rate of change in angular displacement with time, as opposed to a rate of change in position with time. So as we go around this circle, we're going to rotate through 2 pi radians. And the angular velocity is going to give us a measure of how quickly that happens. So it's the number of radians crossed per second. Okay, we give it the symbol omega, and it'll be the number of radians crossed in a given time. And we'll say that in one complete rotation we cross 2 pi radians, and it takes 15.7 seconds to do so. When we calculate that out, we get 0.400 radians per second. Now radians are unitless, they're dimensionless. So we can leave it out and just call this 0.400 per seconds or 0.400 hertz. It's actually the same units as frequency. And it actually calculates out very similarly. We could also call this 2 pi times f, since f is 1 over the period. So we could calculate that either way. One thing to note is that angular velocity is a vector. Angular frequency is the scalar quantity. They're the same number, angular frequency and angular velocity. But angular velocity is a vector. So as we drew this, the direction to the angular velocity is upwards. All right, we're almost there. Part F. Now we want the centripetal acceleration experienced by the block. Because the direction of the velocity is always changing, the speed stays the same, but the direction changes up, over, down, over, up. The velocity is changing. And if there's a change in velocity, there's an acceleration. We'll calculate it as the centripetal acceleration. The formula for the centripetal acceleration is pretty straightforward. The magnitude of the centripetal acceleration is just the magnitude of the tangential velocity squared divided by the radius of the circle, v squared on r. The velocity is 2 meters per second. We'll square that. And divided by the radius, which is 5 meters. 2 squared is 4, divided by 5, that's 0.8 meters per second squared.